Happy Earth Day, and thank you for joining our third program in our four-part series, the Cape Community Water Forum. I am your host, Madhavi Venkatesan. I'm also the founder and executive director of Sustainable Practices. Sustainable Practice is the developer of this Cape Community Water Forum, which is also co-sponsored by the Association to Preserve Cape Cod, Sierra Club Cape Cod, 350 Cape Cod, and the Blue Institute Labs. We are very happy to have Tom Cambareri join us today to discuss the Cape Single Source Aquifer. But before we get started, I'd like to share a few items. At Sustainable Practices, Earth Day is every day, and since 2019, we have been active on the Cape with education initiatives to reduce the impact of the human footprint on our planet. In 2019, we initiated the municipal plastic bottle ban to eliminate town government purchase of single use plastic bottled beverages and the sale of beverages in single use containers on town property. In 2020, we initiated the commercial single use plastic water bottle ban, which eliminates the retail sale of single use plastic water bottles of less than a gallon size, non carbonated, non flavored drinking water. Presently, 13 out of the 15 towns that comprise Cape Cod have adopted the municipal plastic bottle ban, and 7, as of fall town meeting, have adopted the commercial single use plastic water bottle ban. Presently, we have both Bourne and Truro with a municipal ban on their town meeting warrants for this spring, and the towns of Chatham, Dennis, Sandwich, and Yarmouth will be voting on the commercial ban as well. If you have friends or you yourself live in any of these communities, we really encourage you to come out and show your support for these bans with your vote. We appreciate it, and we appreciate the time effort that you put in to learning more about the Cape and learning more about how you can actually be an important steward of our commons. We believe that we can make a difference on the Cape, but we also can be a symbol and an example for the state as well as the nation. Today we have Tom Cambareri. Tom is a water resource specialist and hydrologist. He has 40 years of experience in Cape Cod specific to water resource issues. He has a master's in geology with a focus in hydrology. He is a certified groundwater professional and a Massachusetts licensed site cleanup professional. He is also an appointed member of the Massachusetts Water Resources Commission. We thank you so much for joining us today. There has been so much interest in learning more about Cape Cod's single source aquifer. And with that, I turn it to you, Tom. Thank you.
It's a pleasure to be here today on Earth Day, especially. Who would have thought the poster behind me is an original from 51 years ago. I was just a 15-year-old person at that time, trying to figure things out myself. And at the end of the tumultuous 1960s, there in 1970, we still had some issues. Kent State shooting in Vietnam still going on, but yet good old Richard Nixon passing the formation of the EPA, and in the 70s of all the environmental work that would follow. So anyway, Earth Day was a good teach-in for the world and for me as well. So today I'm happy to be sharing with you some of my experiences and what I've gathered over my years of working, as a private consultant, as a student, and 30 some odd years at the Barnstable County through the Cape Cod Commission and the Planning Commission before that. So my talk will deal with some geology and groundwater, of course, and surface waters and the dynamics of that, and the movement of and how this sole source aquifer feeds all our water resources. So my first slide has to do with the geology, because we need to set the groundwork for our geology. And I was very fortunate to, as a student, to have a professor, Joe Hartshorn, who he was studying geology as the war broke out in Europe, and he joined the RAF. and he started flying planes over the Arctic and became very curious about the formations of that the ice sheets were leaving behind in the Arctic areas. So he became, one of the prominent glacial geologists, and there was quite a few at that time, and I'm quite honored to have studied with them as the first generation of glacial geologists. So I'm not a glacial geologist, but they certainly did have a good time. And I think they were actually, when they started looking, it was Eisenhower's interstate program to build interstates, is that they had to find sand everywhere. So they really had to figure out where all the sand was. And so as professors and doctorates, they took it another mile for us to teach us all about the geology. So we're talking about the Laurentide ice sheet that came down from Greenland and the Arctic, and had its terminus down across Martha's Vineyard in Nantucket as that blue line on the top slide. And that was about 15,000 years ago as it ground south and piled up, accumulated all this dirt and sediments. And in the screen below, you see one of the sequences of how the deposits transition from the right, where is the outwash plain, all the way to the left, which is the moraine. And on the top screen, you can see the retreat, because all the glacial deposits were formed and put down as a retreat from the glaciers. But so as they came back, so we had 15,000 years in Nantucket, and then there's an age dating in Boston around 12,000 some odd years. So we know that's about the time that these carbon dates would put Cape Cod in. And so that there's the moraine, the Sandwich Moraine, and the Buzzards Bay Moraine, and the outwash plains. And one of the interesting things that when you look at those deposits on the bottom there, is what we found out was that actually this moraine was formed by a glaciotectonic process, which the ice sheet receded a little bit more into Cape Cod Bay, and then came back and started to form. So this would be the deposits here that were coming down, and this block, let's pretend that this block is the ice sheet again, and like climate variations, the ice sheet would melt and come back and come back. So this is when the ice sheet came back down, and there's a little hokey music here, I think. And isn't that cool? This is what was happening, at the in the to build up that moraine as the ice sheet came down and piled up those unconsolidated deposits. So very cool. I just found this just the other day. So here we have a more detailed geologic map of the moraine, the Sandwich Moraine, and the several different outwash plains, in the Barnstable Outwash and the Mashpee Pitted Plain, and the large Harwich Plain as well, and then the Nauset deposits. But so they all have they're sequenced in a geologic deposition. And the last, or the youngest deposits, were the Cape Cod Bay Lake deposits that were dammed up against the Sandwich Moraine and the ice contact deposits out in Dennis and Brewster. So what were these deposits? And when we think about that, what do we have? And basically, these are these large foreset beds, they're called. This is a gravel pit that is an exposure of these glacial deposits. And so there's a huge deltaic action going on here that was sorting the sediments out from the the glacier and laying them down in various different layers or stratigraphy, as we call them. You know, some finer grain deposits, very coarse grain. Um, and This is basically what our aquifer is. This is our aquifer matrix as it is exposed. And so what we'd be looking at here is this zone of aeration. There's no water in this, but as it rains and the recharge hits the surface, it starts to accumulate. And what we have is the definition of a saturated zone below this, below our the ground, which is the aquifer. This is the groundwater. It's the zone of saturations of all these sand grains. And there's a water table that's a defined type of surface that you can measure. In this case, with this bucket. And this is the well, and kind of the story of where we get our water is from this aquifer. And so if we figure out that this is a well, now we have plenty of wells, and they're all sorts of diameters, and they're public supply wells, and they're monitoring wells, and they're test wells, and they're all basically going down to the into the zone of saturation. And any child can go to the beach and dig a hole and end up finding the aquifer in a beach or a pondside beach. So no talk about groundwater would be complete without looking at the Cape Cod sole source aquifer. It's actually designated that as a fact of the Safe Drinking Water Act back in 1981. And we have 6 separate lenses of groundwater that make up the Cape Cod aquifer. And we named these the Sagamore lens, which is a term for chief, the chief lens, which is the largest, Monomoy, Nauset, Chequaset, Pamet, and in recognition of the Pilgrims in 1620, over 400 years ago, the Pilgrim lens. And these are water table contours. And the chief lens here, this is about a 60-foot contour above mean sea level. The Monomoy is smaller. This is about a 30-foot contour. Here's about an 18-foot contour, 10, 8, and 5. So the sizes of these lenses are in direct proportion to the land area within them. And these contours, they're all defined by those wells and measuring them and then finding out what that elevation is relative to mean sea level. And what happens in regards to groundwater flow is that groundwater flows essentially perpendicular to these contours. So we have radial flow out from the Sagamore lens to all portions. And there's a groundwater divide that runs through this lens here. So groundwater flows to the north and to the south. And in a similar sense from the Monomoy lens and the Nauset, Chequaset, and Pamet lens. So we have radial flow coming out of all these from the aquifer. And here's a cross section of the aquifer. This is from Cape Cod Bay down to Nantucket Sound. And you see the land surface, and here's the good old water table. And the water table actually has a mounds underneath this a bit. And what are the aquifers defined by the water table, bedrock below at about 300 some odd feet, let's say. We always say kind of an average. And its margins is defined by a zone of transition between freshwater and saline groundwater. And there's various different stratigraphic things going on within the lens. But the basic flow pattern is from the radial part of the top of the lens down out to the sea. And the aquifer is recharged solely from precipitation. There's no underground river supplying us with supplying this aquifer with water. It's precipitation, and so it rains about 40 inches a year on the Cape, and about half of that, or about 27 inches of it, is recharged to the aquifer. And so the recharge is anywhere it rains, it sinks into the ground, goes through that zone of aeration to the water table, and then it seeks its path to ultimately exit at the margins. And it may take uh, hundreds of years for it to go from this zone, and maybe only 5 years from over here. So it's the groundwater flow dynamics. It's the dynamic. It's not one single pot of water that we're sucking the groundwater out. It's actually a dynamic reservoir, or the dynamic source of water, the aquifer. And here's a cross section and of what it looks like out in the outer Cape, and it's because the height of the lens is much less at 20 feet, that the lens itself is only like about 200 feet, and it's underlain by bedrock, which is found hundreds of feet below. So this is a very fragile lens, and when we look at these cross sections, you have to remember that there's a lot of vertical exaggeration. So if this was this distance was a football field, let's say, the lens would be about 1.5 feet thick. I mean, 1.5 feet off off a football field length of, let's say football's length is 300 feet, then the thickness would be about 2 feet in relative to that distance. And so that's why we call these lenses. They're very thin film of groundwater. And so when we look at these schematics, we can say, well, the aquifer is so thick, it's 200 feet long. Well, really, it's relative to the size we have, it's not very thick at all, but thick enough for us. And then, as the ice receded, we go back into this geologic story about the ice receding and leaving blocks of ice as the outwash plain was being deposited by the live ice. And finally, the ice melts all the way back and leaves these holes that we call the kettle holes within the plane of the aquifer. So, I mean, the plane of the outwash plane, or the flat plane. And then you find these holes in it that eventually filled up with water, and these became our ponds. And our ponds, a Cape Cod pond, is a kettle hole. We also call it a window on the aquifer, because it is fed directly from the aquifer, and then discharges down gradient to the aquifer on the down gradient side. So there's an up gradient side and a down gradient side. And we have about almost 1,000 freshwater ponds. 420 of them are named, and 165 of them are greater than 10 acres. And so they get this legal definition as a great pond in the regulations. But they're critical pieces of our Cape, and they're connected to the aquifer, are very dependent upon the water in the aquifer. And here's a perfect kettle hole pond aerial shot of Duck Pond in Wellfleet, with the Atlantic Ocean coming at us in the background. So what about this aquifer and the ponds? The ponds are vitally connected to it, and we're taking groundwater out of it. And we have these groundwater wells that were established, some of them back as far as into the late 50s. My first work started in 1979, and it was my job to go measure 60 wells throughout the Cape, from Falmouth to Provincetown. And this was one of the wells in Barnstable. And so it records the fluctuation of the water table over this period of from the early 60s. And I just downloaded the data yesterday. And so here we are right here. This is the height of the water table right now, in this April. And so how is that, relative to the period of record? Well, you could see that, we're actually kind of on the low side. And that's actually where we are. We're on the low side of normal. And just a year ago, we were hitting some record highs in some areas. So this water table can fluctuate in this particular well over about 5 feet, but in some areas of the Cape, it can fluctuate 8 feet or more. And that has various different manifestations that we can see. One is in the pond shore lengths, and then the other is in putting septic systems in the ground. Is that if you're putting a septic system in the ground and you're digging your hole when the water table is low, you could be putting your septic system in here, but what will happen in the future is that septic system could be inundated. And we came up with this with the U.S. Geological Survey with an equation that we have that's been adopted by all the boards of health, and now it's part of the state Title V system. Is that you need to look at these groundwater fluctuations to determine where exactly how low your septic system can go. So if you're using this well, your bottom of your septic system couldn't be any closer than 4 feet from this spot here, from this height. Very interesting. So what else? We talked about the well that we saw in the zone of saturation, but a new well with equipped with a pump that can pump over 700 gallons a minute, which is 1 million gallons of water a day, creates a drawdown of the aquifer, and it draws the water into the well screen, and it depresses the water table. And this area that is depressed becomes a recharge area. It's not outlined here, but all these wells would have a recharge area. So the recharge area would extend maybe up to here, where this would go into the well, and further up, well, it would go underneath the well. And so this would be a recharge area here. So how does that look? When we look at our public water supply wells, we have about 150 public water supply wells across Cape Cod, and these are recharge areas. So we had these defined by various different methods, groundwater models, analytic solutions, understanding how groundwater flows, and the aquifer, and then so these areas have been recognized and adopted in regulations so that the water quality can be protected in these areas, and so the water quality remains in a good condition. So let's see. When we look at the Cape, there's about 17 public water suppliers, one for each town. We have some that are water districts in green, like they're their own district, and we have some town systems as well. And this one's out of date because now, if you live in the town of Eastham, you now have a public water supply up in Eastham as well. And Wellfleet has a small one for its center over here, but these are the dominant ones through that purveyors through the Upper Cape. And you heard from Dan Pelletier last week, from the area of Harwich. So how much, when we think of what this aquifer supports, and we think about sustainability, like one of the big things is population. And when we look at the population of Barnstable County, from the 1900 to 2020, we see quite a increase of population to where we are now, probably at about 205,000 people year round. And that's just year round population. We know that goes way up, maybe 3 times as much in the summer. And so I pointed out two little spots that'll come up later on in my talk. This 1950 to 2000, and then this area here from 1990 to 2020. So we've got 2 points in time, 50 and 2000, and then a breadth of range from 1990 on. And from 1990 to 2005, this is how much water we pump from the public water supply wells collectively. And so it's about 10 billion gallons of water a year is pumped from the aquifer for our drinking water and irrigation. And 10 billion gallons, that's about 25 million gallons per day on the average. Now in the summertime, that'll go up to over 54 million gallons of water per day. And then the winter, it might go down to as low as 15. So, but the interesting thing that you see across this breadth is our although the amount of water we're taking out is variable, it really hasn't changed that much within the last 20, 30 years here. And that's, when you look at this, it's, you might have expected to see some more increase in this earlier period, but we've been pretty consistent across this zone here. So what about our aquifer? We're pumping all this water out. Now, how much water can you pump out of this aquifer? Well, let's see. Let's look at this chart here first. We have all the lenses named here, and we use these groundwater models. During my time at the commission, I had the great opportunity to manage about 6 different regional modeling efforts, from 1990 to 2020, and the modeling is very useful to us. So what if we look at the totals here? We see that in percent, what happens to the water that in the aquifer, and so about 70% of it just heads out to the coast. And that's in keeping with that first cross section I showed you, where the dynamic flow has water ultimately discharging to the coast. But about 25% of the water is captured by streams. And how much water is taken by the wells? It's about 6% of the water that falls and recharges the aquifer every year is about 6%. And this is a great modeling output that the USGS did for us. And this shows us how the water flows and where it goes. And these blue areas, these dark blue, are the recharge areas to the ponds. Okay, so all these are to the ponds. And about, maybe about in the upper Cape here, it could be as much as 40% of the water flows through the ponds before it gets to streams. And so in green are streams that are groundwater fed. Little Herring River here, Mashpee River. I forget what the name of that river is. Anyway, and then also we have these water supply well zones as well. And so when they do the modeling, these are the water supply zones. And again, this is just an indication of the size of those lenses again, but with some numeric value about how much water is recharged to them per day. So again, so when we talk about how much water we're taking out, it's about 6% of the water is taken out by the wells. And what do we know about what happens to the water after we use it? Well, it goes through our homes and our businesses, and it gets recharged back into the aquifer. So a lot of that water, 85% of it, is recharged back into the aquifer. And that gets into our next section of this talk. But not so fast. What about the future? So we've protected, and we have all these zones of contribution, and protected into as overlay zones in our zoning and all that. Well, what we really need to know: do we have enough water for the future? And so we did this study to look at potential public water supply areas. And if you take out the MMR over there, there's only about 5% of the Cape was left. And this study was actually done in 1990 period, and 5% of that was available for suitable for putting in a public water supply, because as Dan probably told you, putting in a new well, you need to make a lot of criteria and thresholds to get a successful well in. And so a lot of these areas have become the priority open space areas for open space and land trusts to acquire. And even back in the end of 2011 was the formation of the Upper Cape Water Supply Reserve, when it was recognized that the MMR is a huge area for potential public water supply. And that's why the whole issue about the machine gun range up in the MMR, where they're looking at putting a new one in, is so critical, because this is our future water supply area. And I think they want to clear cut another 170 some odd acres, and have various different activities up there. So a lot of this information is just comes to bear, and it makes sense when you start to compare the pros and cons of land use activities. Well, here's another interesting, we've seen a hydrograph before, right? We saw that one in Barnstable. Well, here's a well that we have in Provincetown. And so this well has been measured, and I think you guys can see my cursor. I never said that before, but here's in 1975 up to 2015. And what's going on with this hydrograph is that's different than the others, is that the water table is increasing over that period of time. Now, why would that be? This is a lens that's floating completely on salt water, and the recharge area is finite to the land area. Well, it turns out that this rise, average rise of the groundwater, is equivalent to the sea level rise that occurred during this period of time. So right here, within looking at our groundwater and having these groundwater measurements on a monthly basis for years, again, has been useful for us. And so we did another study with the U.S. Geological Survey to look at, well, what is the sea level rise? What will be the impacts of that on the water table? And so here we have one, let's say, present condition. And we had the survey do the models of the aquifer for 2 foot, 4 foot, and 6 foot level of sea level rise. And so what happens is that the aquifer gets pushed up by the increase of salt water. And so you have more water in ponds, more water going into streams, and then it's interesting that where the streams are, where you'll have more discharge happening from the aquifer as the water table as the aquifer and the water table rise. And if you look at this over the Mid Cape and Lower Cape area, they looked at how much the water table would go up, and it turns out that we were looking at sensitive areas, low-lying areas that were I think about 15% of the land area. No, about 6% of the land area was low-lying areas that are vulnerable. Things were vulnerable, septic systems and things like that were in low areas. And it turns out that the 6 foot sea level rise would increase that area by about 6% more. So we'd end up with 15% of areas that would be inundated by sea level rise. Now, the important, so that's one case, but one of the fortunate things that was found out is that the sea level rise wouldn't have any impact on the water supply wells that were taking water out for drinking water. The wells for drinking water were located too far inland and were too shallow to be impacted by that projection of sea level rise. So now we get into this issue about water quality. And this was one of the first reported um, tests. It wasn't a test actually of drinking water quality, and it was in 1620 when the Pilgrims left Provincetown on one of their explorations, and they found Pilgrim Spring. And we could read the notes of William Bradford, who later became governor, is that they went through the bush and valley and found little paths or tracks. And there we saw deer and found springs of fresh water, of which we were heartily glad and sat us down to drink and drunk our first drink of New England water. So the water quality, our first report of water quality on the Cape was very good. But now what's happened? Well, we looked at the population trends, and in 1950, for the population, you look at the consumption of food and that would to sustain us, and it was about 500,000 pounds of nitrogen produce meat coming over the bridge to sustain us. And in 2000, well, that jumped up to over 2.2 million pounds of nitrogen coming over the bridge for our consumption. And what's the deal with nitrate? Well, nitrate is a drinking water standard, and a lot of our initial work in the 70s was dealing with protecting water quality from septic systems and nitrate nitrogen. And these are reports of nitrate nitrogen in the public water supply wells. And the big threshold maximum contaminant level for drinking water for nitrate is 10 milligrams per liter. And the strategy that we adopted was, well, we wouldn't allow any more than 5 parts per million impact from any new development, hoping that that would keep things, the nitrate levels down. And when we look at the public water supply wells, I think we've done a very good job at that. There's only several wells that are above 2.5, and maybe a handful of wells that ever approach the 5 part per million plantings standard, and none have approached the 10 part per million standard. And this was just looked at again at the APCC water program that they looked at the report cards for the water resources, and they found that the water quality of the drinking water was good. I guess all A's were given out. So we were very successful in our approaches for recognizing where groundwater came from, how to protect it, and keeping it clean. But we look at groundwater, and there's been some impact over time. We compare the levels from 1993 to 2002, and so the cleanest water that we had was near 60%, and now it's down to 40%. And then on the other side, more impacted wells we see more impact from like 25 up to 30 in this zone here. So as good as we got it, and everything is pretty much below 5. There's a handful that are there, but we've seen this kind of transition of what we had before to, well, no, we're getting a little bit more impact. And this is true. This is just a matter of fact of the nitrogen and the larger population, and the fact that we all have septic systems and the nitrate is getting into the groundwater. And what happens over that period of time? Well, we looked at this before, and the groundwater all is seeking its final destination at the saltwater margins. And what happens is that, well, the nitrate ends up in the coastal embayments, and the coastal embayments can't assimilate that load of nitrogen. It's new, it's too much. And we have these large algae outbreaks. And when we look at that, we say, well, you know, here's a recharge area, and this fellow fishing with just the amount of with the nitrogen below this total maximum daily load. That if it goes above that, um, the embayments can't process the nitrogen, and so with more development, uh, the load goes up, and what has happened is that the estuaries become eutrophic. And I talked about the nitrate level here. The 10 part per million is the drinking water standard. Our planning standard was 5. And for marine water, it's less than 0.4 milligrams per liter. So turns out, for all the good work that we did in protecting water supply, it was not good enough for protecting nitrogen. And that's the focus of a whole nother talk that I won't get into any more than this, but it's why we read so much about the efforts to put in to put in not sewers and wastewater management, essentially. How do we deal with our wastewater? How do we reduce the nitrogen loads? So let's have a little fun here now. How does this groundwater move over a period of time? Well, let's see. We've got this sand tank model, and they're going to put in some dye in this sand tank model, and it's going to simulate the flow of contaminants through the groundwater. And what it's actually doing is that is the groundwater flow pattern from that one area to this other one. And you can see this is the dye moving through the porous media of the aquifer. And it moves, this is showing it moving pretty fast. It actually maybe moves about a foot per day on the average. This is a fast action, but you can also see some interesting things happen with the different grain sizes and how the contamination might go around that as well. Here we go. So the groundwater is carrying the dye, which in many cases, in reality, is a contaminant, and you have short flow paths and much longer flow paths. And then you see something really curious happen here. Is what do you see happening when the contamination stops up here? You're seeing the flow go, and the contamination trailing edges on the contamination, with the fact showing out the fact that this aquifer is very dynamic, and that if we stop contamination or clean it up, and we have a chance for it to flush out and get clean. And that's kind of the whole issue of cleanups, and even for wastewater management and stopping the nitrogen from going on. Each one of these could be represented. It could be a major hazardous waste site, or each one of these things could be a septic system as a source of contamination. So it depends on the scale. It can be quite different here, but it's basically the same dynamic. And there it goes, heading out, and it goes from areas of high groundwater elevation to areas of low elevation, until it finally is flushed out. So we can look at well, how does that help us? Well, we spent a lot of time looking at plumes of contamination at the MMR. We started, I think, back in 1992 and 96. It was designated a Superfund site. And these are basically places where the contamination was started or putting in. And these were all solvent sites down in here, and up in the impact area. These were high density areas of artillery shells and RDX and TNT and basically and a lot of RDX and even perchlorate that are form these giant plumes. And that's why we have this $1 billion cleanup operation essentially going on over at the MMR. I just want to talk a little bit about PFAS. And PFAS is polyfluoroalkyl substances. It's the hot new contaminant that a lot of people are talking about. It's a scourge that is attacked, that we've discovered here on Cape Cod. We call these forever compounds. They are in lots of our consumer products and also in aqueous film forming foam. And I became aware of this because one of the things that I did at the county, I managed the fire training academy directly for the Barnstable County Commissioners. And I did that for 28 some odd years. And I had the opportunity to become acquainted in a not so good way with PFAS at that site. And so just a little case study here. If we looked at our zones of contribution and look at this Barnstable area, we have the fire training site here. There's an airport site, the water pollution control site, and these are the public water supply wells around that area. And so I'm going to just show you a little bit about this fire training site up in this area here and try to bring this together here. This is the site and what it looked like back in the 70s. And these were pits where they disposed of petroleum. They didn't dispose of. They put petroleum on the ground and they lit it on fire, and then they would put it out with water. And this site operated from the 1950s on as a training area. And I got involved in 1986 when Superfund and all that came into being, and a test well found oil in the ground. So we put our well in, and we actually found floating diesel fuel about 1.5 feet thick on the lens. And here's the fire training academy here. And lo and behold, it is up gradient. It is near these public water supply wells. So what does a hydrologist do? Well, he measures the water table. And here's the water table contours. And as I said, the groundwater moves perpendicular to these contours. And here's a groundwater model particle path that shows, well, the groundwater will head in this direction. And what did we say? The groundwater moves about 1 foot per day. It would basically take about 3 years for the groundwater to move from the fire training academy to these wells. And here's another the story of the site is rather sad, but here's the site here. These are the public water supply wells. And when I first showed up, we mapped the groundwater petroleum plume from the site that had impacted the Mary Dunn 3 well. And we had to react to this, not only map it, but figure out how to pump and treat it and how to get rid of the soil at the site and stop the source. And just as we were doing that, coming out our back door is this chloroform plume that came from the early Cape Cod potato chips company up on Breeds Hill Road. And chloroform was used in the laboratory. When they would do tests for their oil, they would put a little bit of chloroform in the test. And then, I don't know, they would dispose of it. It was in a septic system. The record of how much they used is they said, in the laboratory, they might have used about 2 gallons worth. And this plume knocked out a well further up gradient and was heading towards another one. So we did this pump and treat. We were able to clean that plume up. And then we were able to clean the petroleum plume. There's some residual left in the ground there, but not too much. It's not a health threat at all. But then we had this other compound. It was MTBE. You may recall that was a additive of gasoline before it was phased out, because MTBE was being found everywhere. So now the ethanol that's in gasoline doesn't last or travel like the MTBE. And then we had a perchlorate plume. Everybody gets rid of their boat flares, but Cape Cod has how many boaters? You have to get rid of your flares after 3 years. And people bring them to the fire departments, and the fire departments bring them over to the training area, and they use them. And we found perchlorate there, and we learned that lesson from the MMR, where they were starting to find perchlorate. So we sampled for it, and we did find it. We cleaned that plume up as well. And now we're dealing with this PFAS plume. And the PFAS plume is a rough outline of that. A lot of study has been done on it. And this is just what had happened in 1966. This is the type of foam that they would use. There's the type of fire that they would set the diesel fuel on fire and practice putting these out. And activities like this happened everywhere across the nation, predominantly in military bases and in airports, because they had to deal with petroleum fires, and so they had to train how to put them out, and they used the PFAS. And this is a mapped plume of contamination of this PFAS, showing it where it impacted the wells. When it was found out that the wells were impacted, those wells were shut down. They weren't used, and now these wells are all treated. And in the town of Barnstable, in the Hyannis area, all their wells now are treated with activated carbon. And so the tests show that there's the water is clean. There's non-detect. There's no PFAS in those wells. But it was about a $50 million collectively effort to get that water in a clean sense. And now when we look at PFAS and we start testing for it, we're not finding any concentrations as high as we ever did at the Fire Training Academy, but it turns out this stuff is pervasive in smaller amounts below the standards. And again, that's the topic of a whole nother study, but I just wanted to bring this together from the aquifer matrix, and how the aquifer works, and how the aquifer feeds our ponds and our wells and estuaries, and some of the cleanup issues that we encountered in trying to restore our drinking water quality, because it is our sole source aquifer. It's the only one we have. And if we cannot have a sustainable achieve a sustainable a way of living with our aquifer here, because this is one of the more bountiful aquifers, in New England. And some people talk about, well, let's have desalinization, or let's do some other things. But we have things that we've done to manage our water supply, and that's the big thing, is like knowledge and understanding your aquifer and how it works is a way to manage it so that it can be a sustainable source for forever. So, they say America runs on Duncan, Cape Cod runs on water, and so for Cape Cod hydrology, some of the big things that I see we need to deal with is the nitrogen from septic systems and groundwater. To deal with that, we need to find locations that are acceptable for wastewater discharges, because if you collect it and treat it, it needs to go someplace. We have to deal with the compounds of emerging concern. As I said, we need to manage our water supplies in concert with these other issues, and potential impacts to surface waters from drawdown, restoring the stream flow to our estuaries and streams that have been manipulated for other purposes. And we need sustained monitoring programs of all this stuff, because if we don't have that information, we can't manage it in a cost-effective way. And I would just make a pitch that Cape Cod really needs a strong regional water resource center as we move forward on all this.
Thank you very much, Tom. I want to thank you so much for your presentation today. We have several questions coming up in Q&A. So as you take your screen down, maybe we can start to answer some of these questions, if you don't mind. Thank you. We have a few in queue, and I'd like to invite anyone else who has questions to please put in your questions within the Q&A box, which you will find at the bottom of your Zoom screen. The first question is related to the lenses that you brought up, and they're basically asking, are lenses connected? Does water move between them?
Water discharges um, to the to the surface waters that separate them. So we have the Bass River, and the Bass River separates the Sagamore from the Monomoy lens. They're somewhat connected underneath, but they're both discharging up into the rivers. So you have Bass River, you've got Blackfish Creek that separates Chequesset from the Nauset. You have the Nauset Creek that separates the Monomoy from the Nauset, and then you've got the Pamet River that separates the Chequesset from the Pamet lens, and East Harbor separates the other one. So they are separate lenses.
Thank you very much. The next question is, when you talk about recharging, does that mean basically replenishment? And how long does it take, or could it be taking until we have depletion of a water source?
Well, that's the great thing about this dynamic aquifer is that the amount of recharge that comes in on an annual basis is is balanced by how much is discharging to the ocean. So the recharge amount is it it's it's a dynamic system that's is essentially equal. Now there are some variations in recharge, and that's why when you look at uh, the hydrographs, the water level graphs that I showed, that you have sometimes where the water levels are really high, and you have sometimes where they're really low. Um, and the pumping of the aquifers, in the models that the USGS has done, is they can look at their model and say, okay, here we are today. This is what it looks like. It's all verified and calibrated. This is the way it works. And then they'll say, well, what did it look? Would it look like if nobody lived here? And they could see what it looked like, and they could say, oh, well, the groundwater was actually 5 feet higher over here or 2 feet higher over there. And so there has been some impacts from public water supply pumping. But when you think about it, a lot of those internal wells is where the water goes, is back. A lot of it's to the development along the margins. So there is somewhat of a decrease. But overall, I don't. We're not in a situation where our water supply would be depleted. But what we need to be watching out for is the quality of it.
Well, this actually ties into the next question, which is, with freshwater ponds dependent upon the aquifer, is there any concern with regard to contamination going from the pond to the aquifer?
Well, you know what? I've seen it. Yes. If let's say what kind of contamination can there be in a pond? Well, there's phosphorus can impact the pond itself, but phosphorus really doesn't travel that far. But when we've seen plumes of contamination going into a pond on the upgradient side, we've also seen the pond discharge it on the downgradient side. So up at the MMR, we have contaminants going into some of those large ponds, the Shumet Pond, John's Pond, and they're mixing in with the water there, and then it's being discharged back. And the thing about these compounds of emerging concern is the level of concern is so low. We talked about 5 parts per million being a planning standard for nitrogen. Well, relative, that would be like 5 million nanograms. And for some of these toxic chemicals, the threshold concentration is 20 nanograms. So it's extremely low amounts, and so we can see those the ponds actually become a source or more distributed. What it does is it takes a plume heading into the pond, it goes into the pond, and then the area of discharge becomes larger but more diffuse.
There's a question related to the $71 million of award money going to the Water Protection Fund. And the question asks specifically, what is the combined amount of monies that are being spent by all Cape Towns, including warrants, if there is such an estimate available, with regard to fund 100% clean water needs for the Cape?
Well, you know what? It's been maybe about 3 years since I've been on top of all those figures, but the cost is significant, and I don't have those right off. But we talked about hundreds of millions of dollars, maybe even what was it? I think it was some estimate. If we had to take the most extreme case, it was $8 billion. But if we were smart about it, if we understood how the aquifer works, if we were very careful and efficient about it, we could reduce those costs collectively to something on the order of 3 billion, 2.8, 3 billion.
Thank you. I have three questions that basically tie to the same thing, which are water utilization rates as well as conservation mechanisms that could actually assist with the amount of water. So one question is asking specifically based on your graphic is, has there been a flat usage of water relative to the amount of water? And the other two questions are related specifically to, can we actually adopt water conservation measures? Is it possible that we may have drought years that will lead to basically rationing of our Cape Cod water supplies?
Yeah,
So there are three parts there. Sorry.
that was. I'll let's get at that final one, because I think that is the crux of it. Is that we already have regulations that deal with the withdrawal of water and its potential impacts on surface waters. Um, Back in 1991, I had there was a fairly severe drought, not as bad as the 1960s drought, but the Mary Don Pond was completely dried up. I had an opportunity to walk across its lake bed and put wells right through it, and found the groundwater about 2 feet below the water, about that pond bed. So this has been recognized in the permitting of the well. So there's something called the Water Management Act, and under the Water Management Act, there are thresholds that look at the hydrographs. So when the hydrographs go below a certain threshold, so you have an average level, and they said when the level is below a 25 percentile range over a period of 2 months, well then mandatory restrictions for pumping, certainly outside water use, would be mandatory. Every once in a while, in the summer, it's just by normal course. You'll see in the paper water districts issuing voluntary restrictions, or watering every other day. It turns out, when we look at the water use over the year, and the summer season is 3 times the off-season amount. And it turns out that it's not all just the population. The larger percentage of that use is for irrigation. So this sets this is why the policies are address that as one of the first things that they can do is to regulate and restrict irrigation. The other things that can be done is potentially putting in private irrigation wells, so that the water districts and departments don't need to run the infrastructure for everybody to irrigate, and to supply water at a drinking water standard for irrigation.
This question sort of ties directly to this idea of utilization rates as well as conservation. What percentage of the distribution is between well water and public water systems? Is there any way to really regulate the amount of draw from private water wells?
Well, I think we're probably at about 85% supplied by public water supplies, and then the other 15 are private wells, predominantly along the outer Cape area. still potentially Eastham that is just building their system, but Wellfleet and Truro. But there are some areas of Mashpee, Sandwich, and Barnstable that maintain their private wells. And I'm not sure what the connection was from that
I
question.
think I think one connection could be, and I'm not speaking for the writer of that question, but it could be related to the idea that you can deplete water sources, as we know that private companies have done to bottle water. So if there's no regulation with regard to the actual amount that a water can be taken out of a private well, that particular entity could help deplete the Cape's water resource. Is that at all possible on the Cape?
Yeah, I think for a single source or person or entity to have that right to take that water out, I just don't see that happening. I don't see that being permitted on the Cape. It is an expensive proposition to locate a well and to put one in and to have it permitted. And this is something that the water districts, the 17, 18 water districts know how to do, and they've done it. And they are regulated. Anybody else that would come in to try to, look at the Cape Cod Aquifer as a source of water to export would be held to the standards of the Water Management Act as well.
One other question is related specifically to the nitrogen load discussion that you had earlier on in your presentation with the
Mhm.
EPA standard of 10 milligrams per liter as a nitrate standard. The question states the Silent Spring has noted that a 1 milligram liter standard should be adopted. And the question is, what are your thoughts?
Hmm. Well, 1 milligram per liter in the wells. So that would mean that um, potentially 60% of the water supply wells, if you go back to that graph, would be over that 1 milligram per liter nitrogen. That would be a big hit. I don't think that's possible. I think what nitrogen in itself isn't a threat at that level of 1 milligram per liter. What I think the writer is referring to is that in cases where you have a discernible increase from background, and 1 part per million is about that level where you say, well, yeah, we're seeing some compromise of the water. It's impaired, not impacted, and it's kind of a subtle distinction. But when the well is impaired with nitrogen with a higher level, well, then you can see of opportunities to see some other types of contaminants. And so the PFAS issue that I was talking about with a level of 20 nanograms per liter, is potentially you start to see other contaminants with an impaired well. So it takes again, the permitting and the regulation under the that requires testing of the wells. And so that's why those Mary Dunn wells were less than 1 milligram per liter, but at a time they had PFAS in it, so they had to be treated. So a 1 part per million standard in and of itself for nitrogen for a well is too extreme, but it should be handled as an indication that you should look for other constituents.
Thank you very much. Now, this last question piggybacks off of the municipal talk that we had last week and asks specifically, is there a difference in terms of the potability testing for well water relative to municipal water, or are they virtually the same?
No, if we talk about well water, and you're saying that's a private well versus municipal water, vast differences. The private wells are not regulated anywhere near as strictly as the public water supplies are. So that's why we've always had these outreach programs. When we started looking at water supply issues on the Outer Cape, we said, everybody, we need to have a program where where we start testing these private wells, because we need to know just exactly, what their levels are. And it turns out once they started the programs and they got the private well people to come in, or they got funding, or they got AmeriCorps people to come in and help out, they saw that, geez, the dense level of development in some of the areas of those outer Cape towns does end up with higher levels of nitrogen, in some cases approaching the and exceeding the 10 part per million standard. And those private wells are often have that variability of impact. And it turns out, from the Silent Spring studies, when they look at private wells, they're much more vulnerable to the other sources of contamination that are essentially from household uses and products that filter into the groundwater.
Thank you very much. Our final question, I'm going to try to say it with some clarity, but they're basically referring to a graphic that you had put up earlier with regard to this discharge. And there's an area where you showed a discharge distribution percentage mix. And apparently there was a data point where it said the discharge to wells was shown as 0% coming from the lens. Can you comment on that? And I forgive me if I haven't made sense in my restating of the question.
I don't recall where that would be in that graph. I think I know what graphic he's or the person is referring to, but I'm not sure which one would be which category was the 0%. Can you discern that at all out of the question?
No, but what we could do is we could offer them, if people have questions, we can tell them to email them to us, and we'd be happy to email them to you if that would work with you, Tom. Because we have actually gone over and exceeded the time that you've committed to being with us today. I really appreciate it. It was a very informative presentation, very thorough, and we had a lot of very good questions. So I'm happy we were able to complement with one another, so give you at one time. But I would like to very much thank you for your time and coming, and I hope that we'll have an opportunity to maintain this friendship with you going forward, because I think there is a tremendous desire, interest to learn more about water, to understand more about how we can protect it and our day-to-day connection to it. And I think you have helped tremendously with regard to at least starting to scratch that surface with our understanding of our daily impact on our water resources. Specifically, I think what has opened up many people's eyes is the impact of what we put on our Cape Cod land and how that affects the areas immediately off the shoreline. I think that was very much eye-opening for many people. So I want to thank you very much again, Tom Cambareri, has joined us this evening. This particular program was put together by Sustainable Practices and our four co-sponsors, APCC, Sierra Club, Cape Cod, 350 Cape Cod, and the Blue Institute Labs. And we thank you all for joining us this evening. There is a survey form as you leave. We greatly appreciate your answering those questions. And we look forward to you next week for our final program, which will be with Blue Institute Labs, talking about specific emerging technologies to deal with some of the issues that Tom has surfaced today. So thank you all very, very much.
Pleasure to be with you.